This is Fundamental Identities and Proving Trig Identities. In this section, you're going to see that we're going to be working a lot with our trig identities, and very often, more than not, it is very, very similar to geometry when we are doing proofs. So the first thing that we first have to understand are the actual identities. So on this slide, we can go ahead and take a look at our quotient, reciprocal, Pythagorean, and even odd identities. Quotient identities we've been working with for some time. Notice tangent is sine over cosine, and your cotangent would just be the inverse of your tangent, which is going to be the cosine over sine. Reciprocal identities is whenever you have a single trig function, you are going to do the reciprocal of it for its inverse. So in the case over here on the left-hand side, we can see that cosecant of theta is equal to 1 over sine theta. Now the same can be done if we were looking at sine theta. Sine theta would actually be equal to 1 over cosecant theta. Now this is extremely important because this gives you the ability to go ahead and change the way an equation looks by replacing it with something else of its equivalent. This can be done with sine, cosine, tangent, as well as cosecant, secant, and cotangent. Let's take a look at Pythagorean identities. Here you're going to have 3 different equations, and depending on what we see within the equation, we can go ahead and alter these equations to make sure that they give us what we need within the equation we are looking for. So, in the first example, we're going to go ahead and take a look at sine squared theta plus cosine squared theta is equal to 1. Now there are multiple different equations that could be created from this one identity. For example, if we were to isolate sine squared theta, we would have sine squared theta is equal to 1 minus cosine squared theta. Another possibility of an equation that we could have would be cosine squared theta is equal to 1 minus sine squared theta. Now, any one of these could be used within an equation. The number one thing to remember is the actual identity itself, and you would be able to manipulate it later on depending on the equation and what is being given within that equation. Our even odd identities, here we have them split up into families, meaning sine and cosecant, cosine and secant, tangent and cotangent. Now, if we were to split this up, you can easily see that our sine family as well as our tangent family behave very similarly. When the negative from theta comes out, it goes to the front of the trig function, making the entire thing negative. So sine and cosecant would then turn negative, tangent and cotangent would turn negative, and cosine would be the only one, or cosine and secant would be the only ones that would actually turn to be positive. This is one of the easier ways to remember these processes, but there are many more that you can use. Slide 3 goes over, once again, even and odd identities. And slide 4 goes over the general strategies for proving an identity. Keep in mind, the entire goal is to make sure that you are making it known that the equation you're looking at is an identity. So as we start working with some of these equations, there are certain types of processes that you will see you will have to use. The first suggestion, number 1, work with the more complicated expression, and work towards the least complicated expression. This makes it easier for you to be able to work with your equation and break it down as it gets easier. Number 2, if no other move suggests itself, convert the entire expression to one involving sines and cosines. Now, initially you want to use all of the possible identities that you can, but if you have no other choice, make sure to use sine and cosine wherever needed. Number 3, combine fractions by combining them over a common denominator. There will be times where you're going to need to either add, subtract, and it will be with different denominators. This would be very similar to just adding and subtracting regular fractions that have unlike denominators. Step 1 would be find the common denominator, create your new numerators, combine your like terms, and create your new expression. Step 4, or number 4, use the algebraic identity of a plus b times a minus b is equal to a squared minus b squared. This is your difference of powers. Now, as you're working with this setup, generally it's going to lead you and it's going to set up the problem to be able to use the Pythagorean identities later on. So it's extremely important to be able to spot that whenever you have the difference of these equations, it will eventually lead to your Pythagorean identities. Number 5, always be mindful of the target. So you want to go ahead, you want to make sure that you have an eye on the prize as far as what you are trying to get close to, and you're consistently trying to make it as close to that answer as possible. Let's begin with slide 5. Now, whenever you have an equal sign in your problem, what's going to happen is that you are going to try to convert the left side to look like the right, or the right side to convert like the left. It is completely up to you, but just keep in mind some options are easier than others. First one that I would suggest to work with would be the left and convert it to make sure that your answer looks like that of the right-hand side. So we will begin with tangent. Now we know that tangent is the same as sine of x over cosine x. And we know that cotangent of x is cosine x over sine x. Here we are running into an addition of fractions with two unlike denominators. First would be find the common denominator. In this case, cosine x, sine x would be our common denominator. You go ahead and create your new numerator. You can see that cosine x and cosine x would cancel off. You're left with multiplying your old numerator by sine x. This leaves you with sine squared x in your numerator. You're going to do the same thing for the right-hand side. Sine x cancels with sine x. You're going to multiply by cosine x. And you're going to be left with cosine squared x. Now this leads us back to one of our identities. Once we combine these two fractions, because they have a common denominator, you're going to see that we have sine squared x plus cosine squared x over cosine x sine x. Our numerator is actually equivalent to 1. So what we're going to do is we're going to rewrite this problem with 1 in its place, cosine x sine x. In this case, we can go ahead and use the reciprocal identity, 1 over cosine x would give us the same as secant x. And 1 over sine x would be the same as cosecant x over 1. Notice in this case, our final answer would be secant x cosecant x. Now this is the same as our right-hand side, which is exactly what we wanted to do. Let's go ahead and take a look at our problem on the right-hand side. So, with this problem, first step that you want to take a look at and realize is that we're going to be working with a difference of squares. Now, when this happens inside of a denominator, it actually is called your conjugate, and you are going to multiply both the denominator and the numerator by the exact same term, but with a different sign. By doing that, you are then going to put yourself into a position where you will be able to go ahead and use the identities in the problem. So first thing would be multiply your numerator, so the cosine of t times 1 plus sine x, sorry, not x, t, over 1 minus sine squared t. From there, we're going to go ahead and convert our denominator to its equivalent, which would be cosine squared t. Since our numerator will be remaining the same for now, cosine t times 1 plus sine t. Keep in mind, our cosines are actually going to cancel out. In this case, the numerator cosine t will cancel with the square of our cosine from the denominator. In this problem, we're actually going to end up with 1 plus sine t over cosine t. Keep in mind, it matches up with the right side, which means we have done this problem correctly. There's another type of problem that we're going to take a look at in slide 6. In slide 6, now we are taking a look at a problem in which we are then not having an equal sign in between our two sides. We just have an expression. And the entire goal behind this expression is to simplify it the most that we possibly can. So let's take a look at the problem on the left-hand side. Our first step here is to take out a greatest common factor of cosine x. Once we do that, we're going to be left with cosine squared x plus sine squared x. Now in this case, the identity that we see on the right-hand side or inside of the parentheses is equivalent to the value of 1, which means when we rewrite this, it's going to be cosine x times 1. And when we multiply it fully out, our answer is going to be cosine x. Let's go ahead and take a look at the next one. Once again, we are looking at a difference of squares for this numerator. Now, just as we saw in slide 4, it said anytime that it is used and we are working with a difference of squares, it will usually lead to one of the equations from the Pythagorean identity. So we're going to go ahead, we're going to multiply these two terms against each other. We're going to end up with cosecant squared x minus 1 over our denominator, which is cosine squared x. We know that the numerator itself is one of the identities, and it is equal to cotangent squared x. In this case, we are going to rewrite our cotangent squared x as our cosine squared over sine squared. Keep in mind, we have not changed the problem underneath our cotangent squared x. So it would remain as cosine squared over 1. This gives us the ability to see that we are working with two fractions, and we are going to keep change flip in order to make sure that everything is simplified. So cosine squared x, so we have cosine squared x over sine squared x times 1 over cosine squared x. In this case, our cosines simplify out, and we're left with 1 over sine squared x. Keep in mind, we can use the reciprocal identity to provide us with cosecant squared x as our final answer. Let's go ahead and take a look at slide 7. So in slide 7, once again, we are taking a look at a problem on the left-hand side that has the difference of squares. We're going to go ahead and begin with that portion. That will leave us with secant squared x minus 1 over sine squared x. Now we know that secant squared x minus 1 is actually equivalent to the tangent squared x. So we're going to go ahead and rewrite it. Tangent squared x over sine squared x. Tangent is equivalent to sine over cosine. So sine squared x over cosine squared x. And we keep the denominator as original, sine squared x over 1. We're going to keep change flip. So sine squared x over cosine squared x times 1 over sine squared x. In this case, sine squared x will cancel out from both sides. We are left with 1 over cosine squared x, or 1 final answer of secant squared x. Let's take a look at the problem on the right-hand side. For this problem, notice our denominators are different, and we are going to have to multiply them in order to get that final answer. When we do that, our new denominator is going to be cosine x times 1 minus sine x we're going to go ahead and figure out our new numerators. These two denominators will cancel out. We're left with cosine x times cosine x, which will leave us with cosine squared x. On the right-hand side, cosine x cancels out. We're left with multiplying it against 1 minus sine of x. When we do that, remember we need to distribute the negative to each one of our terms. We're going to be left with sine x plus sine squared x. We combine everything over the same denominator. So cosine x, 1 minus sine x. All of our terms will then be combined together. So we have cosine squared x minus sine x plus sine squared x. Now, us having cosine squared x and sine squared x, when we combine those two terms with each other, we end up actually getting a solution or an equivalent value of 1. So this numerator will then turn into 1 minus sine of x over cosine x, parentheses 1 minus sine x. In this case, our entire numerator simplifies with our denominator from the inside of the parentheses and gives you 1 over 1. We multiply straight across. It's going to leave you with 1 over cosine x, which is the same as secant x as a final answer. This helps to go over the entire PowerPoint for this section. Highly suggest go back, work on the problems, write down your identities, and make sure that you know them by heart. If you have any other questions, please feel free to reach out.